In this video, we're going to talk about higher order derivatives and velocity and acceleration. The second derivative of y equals f of x is the derivative of y equals f prime of x. So in other words, we determine the first derivative, then we determine the derivative of that to get the second derivative. In Newton notation, which we tend to use more often in this video, the second derivative is expressed as f prime prime of x. In Leibniz notation, we refer to the second derivative as d2y over dx squared. Now, displacement is like distance, but with a directional component as well. And in this video, we'll see that sometimes displacement will be negative. So if we include that positive or negative directional component to distance, we get something called displacement. And the displacement, as it says up at the top of the slide, is the position of an object with respect to time, usually referred to as s of t. Velocity is the rate of change of displacement over time. Similar to how speed was the rate of change of distance over time in earlier grades, well, velocity is the rate of change of displacement over time. So it will have a directional component. In this slide, in this video, we'll sometimes have negative velocity or positive velocity. The first derivative of the displacement function with respect to time is velocity, as we said. So in other words, v at t is s prime of t. And acceleration is the rate of change of velocity over time. So it's like the rate of change of the rate of change. That makes it a second derivative. So like it says on the slide, therefore, the first derivative of the velocity function with respect to time, or the second derivative of displacement with respect to time, is acceleration. So in other words, a of t is equal to v prime of t, or s prime prime of t. And so we have it written here one more time, just for clarity. Velocity is the rate of change of displacement over time, and acceleration is the rate of change of velocity over time. Now, negative velocity means an object is moving in a negative direction, which could be left or down. If we're on a horizontal line, we tend to think of left as being negative and right as being positive. If we're on a vertical line, we tend to think of down as being negative and up as being positive. Okay, second bullet point, zero velocity means an object is stationary, but interestingly, that's where change in directions often occur. If we have velocity of, let's say there's a baseball and it's going up and then it reaches a maximum height and comes down, at that moment where there was a change in direction, the velocity stopped being positive and started being negative. Well, there was a brief instant at that change in direction where the velocity was equal to zero. Third bullet point, the negative acceleration means velocity is decreasing, while positive means velocity is increasing. Zero acceleration means velocity is constant. Now, slightly different than velocity is speed. In the fifth bullet point, it says the speed of an object is the magnitude of its velocity. And in the last bullet point, we say that an object is increasing in speed or speeding up when velocity and acceleration have the same signs. So if velocity and acceleration are both positive, we see that the speed is increasing. But we can also say that if velocity and acceleration are both negative, we're speeding up in reverse, so to speak. And so the velocity is increasing in magnitude while still being negative. So the magnitude of its velocity is increasing, so we say that it's speeding up if the velocity and acceleration are both negative. But if an object has positive velocity with negative acceleration, it's decreasing in speed. And similarly, if it has negative velocity but positive acceleration, it's also decreasing in speed. Displacement is measured in meters and time is measured in seconds generally. So we generally say velocity is measured in meters per second and acceleration is measured in meters per second squared. So let's get into some examples. In this first one, we want to determine the second derivative simplified of this expression. And so First, we'll do that, and then we'll worry about what it equals when x equals 1. So in order to determine the second derivative, we need to determine the first derivative. We're going to use the quotient rule on that expression right there. So we have the derivative of the top times the bottom minus the top times the derivative of the bottom all over the denominator squared. When we simplify that, we get 1 over 1 plus x quantity squared. That's the first derivative. Now, like it says here, we like to simplify that first derivative before determining the second derivative. We could have used just a straightforward quotient rule to determine the derivative of the derivative, but personal preference, I like to make a chain rule out of it. So turning this into 1 plus x quantity to the negative 2, I can then determine the derivative of that, which will be negative 2 times 1 plus x quantity to the negative 3 times the derivative of the inside of that bracket. So we end up with negative 2 times 1 plus x quantity to the negative 3, or in other words, negative 2 over 1 plus x quantity cubed. That's what f prime prime of x is equal to. Now, at a value of x equals 1, we simply plug in a 1, and we get negative 2 over 8, which simplifies to negative 1 over 4. So the value of the second derivative at x equals 1 is negative a quarter. Now, for example 2, we have a baseball being hit vertically upward. What we're going to say is that as this baseball goes up in height, its velocity will be positive and its displacement will be increasing. As it starts to come down, we'll say that it has negative velocity. We want to determine the maximum height reached by the ball, and then we also want to determine the velocity of the ball when it's caught 1 meter above the ground. To determine the maximum height, what we're going to do is determine at what moment was the velocity equal to 0, because at that moment of maximum height, our velocity goes from positive to negative. So for a brief instant, it crosses over a moment where the velocity is 0. We're going to figure out when that is. So the ball reaches its maximum height and immediately changes direction. Our strategy, therefore, will be to determine when the ball changes direction. As discussed earlier, the ball changes direction when velocity is 0. Therefore, our first move will be to determine when the velocity is 0. Well, since s at t is negative 5t squared plus 30t plus 1, therefore v at t will be negative 10t plus 30. Letting v at t equal 0 implies negative 10t plus 30 equals 0, so t is 3. So all we have to do now is to determine what's the displacement at that moment when t is 3. So since displacement is given by this equation up here, we just plug in a 3 for t, and we get an answer of 46. So the maximum height reached by the ball is 46 meters. In order to determine that, we had to figure out when it occurred, but that was our strategy. Now, to answer part B, we want to know what's the velocity of the ball when it's caught 1 meter above the ground. Well, in order to do that, we're first going to need to determine when the ball is 1 meter above the ground. Well, 1 meter above the ground is an indicator of position, and position is given by displacement. So what we're going to do is we're going to say, let's let s at t equal 1. And then what we're going to do is we're going to solve for t. So if we let 1 equal that expression for s at t, we then see we have a higher order equation, and so we're going to let it equal 0. There should be a t here. Actually, there's a little typo, missed a t. But we see that 0 will be negative 5t squared plus 30t, and so that'll be negative 5t times t minus 6. So if I let 0 equal negative 5t or 0 equal t minus 6, I get that t is either equal to 0 or 6. Now they're specifically asking me when the ball's caught. That's going to be the second of those two times. The first time, the time equaling 0, it will be the moment when the ball is hit. The time equaling 6 will be the moment when the ball is caught. So Let's figure out the velocity at t equals 6. Plugging in t equals 6 right here, we get negative 10 times 6 plus 30, which is negative 30. So therefore, the velocity of the ball at that moment is negative 30 meters per second. We're not surprised to see the velocity be negative because the ball's displacement way up at the top is 46. By the time it gets to the bottom, its displacement is decreasing down to 1. So we're not surprised, since we're losing displacement's getting less and less, to see that our velocity, the rate of change, is negative. So we can say that our velocity is negative 30 meters per second, or sometimes you'll see it written 30 meters per second, but specifically saying downwards. Now, for example 3, we're going to look at an object moving on a line given by this formula right here. And we're going to answer a series of questions about that. The first question will be to determine the velocity and acceleration of the object when t is equal to 2. That'll require us to determine a first derivative and a second derivative. Now, before going any further, it would be nice if this question told us whether this line is horizontal or vertical. We don't know which way it is, so we'll try to accommodate for that in our answer. But answering part A first, we see that the velocity will simply be equal to the first derivative of displacement with respect to time. We simply employ the power rule on the expression 6t squared minus t cubed. We get 12t minus 3t squared. Then our acceleration is the derivative of that expression, 12t minus 3t squared, which is just 12 minus 6t. So now that we've got the velocity and acceleration expressions, we just have to sub in a t value of 2. When I let t equal 2, velocity is 9, and when I let t equal 2, acceleration is 0. I like to put of course, it's important to put the units in, so we can say that our velocity is 9 meters per second and our acceleration is 0 meters per second squared at that time. Now for part B, it says, what time is the object at rest? An object at rest, the implication is that the velocity is equal to 0. Well, in the previous slide, we determined that velocity was given by the expression 12t minus 3t squared. So we're saying that the object is at rest when that expression equals 0. So we simply factor 3t times 4 minus t is equal to 0. And so that means t would be either equal to 0 or 4. So the object will be at rest at a time of 0 seconds or at a time of 4 seconds. And that's our answer to part B. To answer part C, we want to indicate what direction is the object moving at t equal 5. Well, what we're going to do to determine direction of movement is to determine if the velocity is positive or negative. So again, we have our velocity expression from the previous slides. We know that velocity is equal to 12t minus 3t squared. And so we're just going to let t equal to 5 and evaluate that. When we do that, we get a velocity of negative 15. That's meters per second. So, like it says, since the velocity is negative, the ball is either moving to the left if the line is horizontal, or to the it says or to the right if the line is vertical. That should say or down if the line is vertical. A little typo there. So if we have a horizontal line, the ball's moving to the left. If we have a vertical line, the ball is moving down, because both of those are indicators of negative velocity. Okay, to get to part D, this is kind of an interesting one. Is the ball moving towards or away from the starting point at that time? Well, let's think about this for a second. We'll use a horizontal line analysis, but the exact same analysis will work if we think of it as a vertical line. First thing we want to do is to determine what the starting point is. So the starting point is the displacement at a time of t equals 0. So figuring that out is relatively straightforward. We just let t equal 0 and evaluate s of t, and we see that that is equal to 0. So we have a starting point of 0. Now, We then want to think in terms of that number line that we have down below. And like it says here, if the displacement is negative and the velocity is negative, we'll have the situation indicated at the bottom. The object would be to the left of the starting point and moving towards the left. The object would thus be moving away from the starting point. On the other hand, if the displacement was negative but the velocity was positive, we'd have the situation indicated now, where the object is to the left of the starting point but moving toward the right. The object would thus be moving towards the starting point. On the other hand, we could have a displacement that's positive and a velocity that's negative. And if that was the case, the object would be to the right of the starting point and moving toward the left. The object would thus be moving towards the starting point. And finally, if we had a displacement and a velocity that were both positive, the object would be to the right and moving toward the right. The object would thus be moving away from the starting point. So to sum it up, what we want to do is figure out what is the sign of our displacement and what is the sign of our velocity at the moment of t equaling 5. Okay? If the displacement is 0 and velocity is non-zero, the object would be moving away from the starting point. And if the displacement is 0 and velocity is 0, the object's neither moving away nor towards it. Okay, so what we do, like we said, we're going to figure out our sign of both our displacement and velocity. At a time of t equal 5, our displacement is positive and our velocity is negative. So we have a situation indicated in the diagram there. Positive displacement, negative velocity. The object's moving toward the starting point at that time. Now for part E, it says, when is the object moving in a positive direction? Well, direction of movement is related to velocity, like it says in our solution. So the object is moving in a positive direction when the velocity is positive. So v at t greater than 0 implies 12t minus 3t squared is greater than 0. So in other words, 3t times the quantity 4 minus t would be greater than 0. Now to solve that higher order inequality, we do interval testing over intervals to see where the quantity is positive. So what we do, we have one side equal to 0. I'm going to make a number line. I'm going to indicate each value of t that makes the expression on the left equal to 0. So that would be t equals 0 or t equals 4. This is the number line that I've drawn at the bottom of the page. And now what I do is I can pick a representative value within each interval to test. So for instance, when t is less than 0, I can simply pick any number less than 0 that I want. Let's say t equals -1. I let t equal -1, and then I determine whether the expression 3t times 4 minus t is positive or negative. That I would see there that expression would be negative. So I have a negative in the region to the left of 0. In between 0 and 4, I pick any value in between 0 and 4 that I want. Let's say I let t equal 2. And then what I do is I plug that value in for both the 3t and the 4 minus t, and I see if I get a positive or negative result. We see here I get a positive result. And finally, I can let t be any value to the right of 4. And let's say I let t equal 5. If I let t equal 5, then 3t is positive, but 4 minus t is negative, making my overall result negative. And so I get the result shown in the number line at the bottom. And so I've got a negative, positive, and a negative. Now, to be honest with you, we know t has to be greater than or equal to 0 for a couple of reasons. One, common sense. T is referring to time. But two, it actually says it here. So we're not even going to really consider that interval at all. And so we can see that our object is moving in a positive direction in this interval right here, in between the 0 and the 4. And so we say when 0 is less than t is less than 4. We don't want to say less than or equal to t, less than or equal to 4. That would be wrong, because at a time of 0 and at a time of 4, the object is at rest. And so it would be wrong to say at either of those times that it's moving in a positive direction. And finally, the last question, F, says, when does the object return to its initial position? Well, it's important to figure out what the initial position is. We do that by letting t equal 0 and plugging it into the displacement expression. When we do that, when we let t equal 0, we see that the displacement is actually 0. So what the question's asking us is, when is the position of the object 0? In other words, let s of t equal 0 and solve for t. When we do that, we get t squared times 6 minus t equal to 0, which means t is 0 or t is 6. Now the question asks when the object returns to its initial position. Therefore, we're going to say at a time of 6 seconds.